Okay, now we are going to discuss uniform circular motion. So, what is uniform circular motion? Let's say there is a body and this body is moving on a circular path. Hmm. Okay, so this is the circular path, and let's say this is the center of this circular path, and the body is moving on this path. If this body moves with a constant speed, uh, be careful about that. Speed is constant, that is, the magnitude of the velocity is constant. Suppose here the particle has or the body has velocity of something v, here the body has velocity of something v prime. So these two velocities, or you can take any other point. So these two velocities have equal magnitude. So this kind of motion, circular motion, we can call uniform circular motion. Here speed is constant, but the velocity, this is not constant, because at each and every point the direction of the velocity is changing consistently. So if velocity is changing, then there should be an acceleration which is causing this velocity change. So we are going to discuss about that acceleration and the magnitude and direction and all about that acceleration. So let's go to the next point. Okay, let's say the position vector, we are taking this center to be origin or reference point. So the position vector for this point, let's say this point is P, is R, and let's say this point is P prime. So position vector for this point P prime, let's say this is R prime. So what is happening here? If we want to know about, well, acceleration, so this acceleration should be equal to change in velocity by change in time. Let's say from point P to point P prime, the body has taken time of delta t. Okay, so from here we can see one thing: the direction of acceleration is along the change of velocity. Here we can see this thing. This is acceleration vector, and this is a scalar quantity, and this delta v is a vector. So the direction of this acceleration should be along the direction of change of velocity. So how can we uh, proceed to find this direction? So let's take another diagram. So here we have the diagram from NCERT book. So what is happening? This is v prime, and we know we can translate a vector without changing its magnitude and without rotating it. We can translate a vector from one point to another point in the space. So what is happening here? Let's say this v prime vector is translated to here, and this v vector is translated to here, and so that their uh, tail can be joined at a point. So we can see now, for a circular motion, at any point velocity is tangential. What I am trying to say, actually, if you are taking a point here and you want to know what is the direction of the velocity of this body which is moving on a circular path, so this velocity is tangential. You can say it is making a right angle with this radius. So here we have this velocity perpendicular on this r prime vector, and this velocity v perpendicular on this r vector. So if these two velocities are perpendicular to these two position vectors, we can say one thing. We can say that if this r position vector is being rotated by an angle delta theta, this velocity vector will also be rotated by the same angle. As this velocity vector is always perpendicular to this position vector r. So if position vector changes its orientation from this location to this location, and while changing this orientation, it is moving by an angle delta theta, let's say, then this velocity vector, which is always perpendicular to the position vector, will also rotate by this delta theta angle. This is what drawn here. So we have v prime, and then we can say this is change in velocity. So along this direction was the initial velocity, and now new velocity has direction along this. Then we can say this is the change in velocity. You can take it easily. This is one vector, this is another vector. So uh, let's say this is vector B, this is vector A. So you can say vector A minus vector B, that is change in this these two vectors difference. You can say this will be represented by this vector. This is vector A minus vector B. This is what drawn here. So we have change in velocity vector now, and we can see very clearly here this delta V vector is directed along the center. We can take another diagram for the example purpose. Let's take this diagram. This vector V prime is being translated, and this vector V is being translated here. So again, we can see after the moving these two vectors, we have delta V here, and this delta V is directed towards the center. So what is happening? The direction of delta V is towards the center. It means the direction of acceleration should be towards the center of this circular track. Okay, along the radius, or radially towards the center, radius, and towards the center of this circular path. And for this conclusion, you can give another argument like this. This is vector r, this is vector r prime, and this is delta r. So these vectors are r, r prime, and this vector is delta r. Now, at each and every point, this v is perpendicular to r. Then this r prime and this v prime, these two are also perpendicular to each other. Then with the same argument, we can say this delta r and this delta v should be perpendicular to each other. Means the delta v should be perpendicular to the delta r. And this delta r is nothing but chord of the circle, this circular path. Then if there is some perpendicular, let's say line segment or line or vector through a chord of a circle, then it should pass through the center. This is what happening here also. So this delta V is perpendicular to delta R, and if this delta V is perpendicular to delta R, it should pass through center. Now, whether it is towards the center or away from the center, this we can simplify by just observing this diagram. So if initially the direction of velocity was this, and after the change its direction comes here, means towards, let's say this is the new velocity vector. So there should be acceleration along this direction, and for each and every point, if we are going for another diagram here also, you can see very clearly, if initial direction of velocity was this, and then after change it comes like this, the acceleration should be inward in the sense with reference to this point. So first, the direction of change of velocity is radial. Second, it is towards the center. Let's move on and go for its magnitude. Okay, so acceleration should be delta V divided by delta t. We have just discussed about direction of this acceleration. Now we are moving to find its magnitude. So if this is a kind of average acceleration, and here we are taking acceleration to be constant, because if the acceleration is changing, then the path of the movement of this body will no longer be a circular path. So let's say this is a, we can discuss this thing later, but for now we are taking this acceleration to be constant. constant in terms of its magnitude. So this is delta V divided by delta T, and we are taking magnitude now. So this is average acceleration, and average acceleration is constant. Then at each and every point, the acceleration has the same magnitude. So if we want to get the magnitude of acceleration at any point, we have to take limit. We have to take limiting factor like limit delta t tends to 0. Means we have to reduce this time interval as short as possible. So let's go to next diagram, then we can get it. So this is acceleration radially inwards towards the center, and this acceleration we can simply give as at a point. Let's say at point P, what is the acceleration? We can say this is delta V, but now we are taking this delta t to be tending to be 0. Only then we can get instantaneous acceleration at any point, not an average. Although here average and instantaneous both acceleration are same. So this way we can find the magnitude of this acceleration. Next, how can we proceed? So we have to go to the previous diagram. Let's take this diagram. Okay, here we have one triangle, this one C P P prime, and here we have another triangle. We can write it G H I. So these two triangles are similar. How I'm saying this thing? This is delta theta, and if this position vector is being rotated by delta theta, this velocity vector will also rotate by the same angle delta theta. So one angle we can say this angle at this vertex C and here angle at this vertex G. These two angles are equal in these two triangles. Now coming to next. This is r prime and this is r. These two are position vectors, but their magnitude is nothing but the radius of this circular track. So if we are taking what is the magnitude of vector r, it should be the radius of the circle. And if we are taking what is the magnitude of this r prime, it is also the same radius of the circle. So if these two are equal, the angles in front of them should also equal. Let's say this angle is something x, so this angle should be x. And as we have discussed earlier, in uniform circular motion, the magnitude of velocity, that is speed, it remains constant. Means the length of these two vectors is equal. Only they are differing in their directions, but their magnitude is same. Speed is same at each and every point on this circular path. So if this angle is x, this angle should be x. Now we can see these two triangles C P P prime and G H I. These two triangles have all angles correspondingly equal. So we can say these two triangles are similar. And if these two triangles are similar, we can take their we can take ratios of their sides. So how can we take to get some result? Okay. So let's take this triangle first, CP P prime. Here we can write delta R divided by anyone R or R prime, no matter because magnitudes will be the same. And here in this triangle, correspondingly, we can take delta V divided by V. So these two triangles C, P, P prime and G, H, I, these two triangles are similar. So we can take their ratios of their sides. And these two things should be equal. So this is basic mathematics. Okay, let's write this expression somewhere else so that we can do some calculation. So this is delta R and this is R and equals to delta V divided by V. We are taking magnitude, so simply we can write delta R by R. We can write here capital R, which is the radius of the circle, equals to delta V by v, which is magnitude of the velocity, or you can say speed of this body or particle which is moving on circular track. So this delta r we can write equals to delta v by v and into r, capital R here. Now we have to make an assumption, or we can take it as, let's say this uh, delta theta is very small. This delta theta is very small. So this is r and this is r prime. Then we can write this length. Let's say this is delta s for a moment. We can write this thing. We can write this thing delta s nearly equal to delta r. So, okay, let me go to the previous diagram. There it will be more clear here. Okay, so here delta r is this length, and delta s is the arc on which the particle moved from point P to P prime. So this arc is delta s. Okay, and if we are taking this delta theta to be very small, we can say delta r is nearly equal to delta s, and delta s is nothing but the speed into time interval. We can write it delta s, or we can write it delta r. So this way, delta r equals to v into delta t. We can write for a moment. So let's move. So this delta v and this delta r, okay, we can write this thing in another way. Uh, let's rearrange the terms. So after rearranging, we will get uh, delta r into v divided by capital R equals to delta v. And now, if we are dividing both sides with delta theta, sorry, delta t, so we will have delta v by delta t equals to delta r into v divided by delta t into capital R. And now we can take limit so that we can get acceleration at a point. So this is delta v by delta t, and delta t is tending to 0 equals to delta r by delta t, and delta t is tending to 0, and then we have constant terms v by r multiplied with. So this thing is nothing but acceleration. This thing is nothing but velocity or speed, you can say, if we are not taking direction, speed, and then this is. So finally we have this acceleration equals to v square by r. This acceleration we call centripetal acceleration, and we used to represent this by a c. Why centripetal? Means it is acting towards the center. It is just kind of center seeking acceleration. Here we can see it clearly. This acceleration is acting towards the center. That's why we call it centripetal acceleration. Okay. So up to here, we have got the magnitude of this centripetal acceleration. So although we are discussing uniform circular motion, we have taken only those things which are in linear motion. Actually, we can see here uh, this velocity is for linear motion. This position vector or change in position vector, that is delta r. This is also for linear motion. So we have taken only those terms which are related to linear motion. Let's carry on our discussion and move to circular motion aspect. So what is how can we go for that? For that, we need to know that this angular position, change in angular position, that is delta theta, we can write this is r prime, and this point is c, and this is vector r. This was point p, and this was point p prime. So we can write, if the time taken to move from point p to p prime is delta t, we can say the angular speed will be delta theta by delta t. And we can use direction also using Maxwell right hand thumb rule, that we will do later. But for now, we are taking only magnitude of this angular velocity, that is angular speed. So we can write this angular speed to be delta theta by delta t. And now this is delta theta and this is delta r, and this arc is, let's say, delta s as we have taken earlier. So for very small delta theta, we can write delta r nearly equal to delta s. Then delta theta will be, this will be delta theta will be this one, delta s by this r. You can write delta s by this r. As we know, if for a small angle, if this is L, this is R, and this is theta, this theta will be L by R. So the same thing we are taking here. So delta S divided by this R. Now delta S will be R into delta theta. So we can write V equals to delta S divided by delta T, and this we can write R into delta theta by delta T. But delta theta by delta T is nothing but angular speed. So we can write this linear speed is related to angular speed as follows. We are just taking magnitudes only. We can discuss about the direction term because angular velocity or linear velocity, these are vector quantities. So there should be vector space, but we will discuss those things later. So this V equals to R into omega. Now we have connected this linear velocity with the angular velocity, and then we can carry forward the same thing to this acceleration. So we can write here this centripetal acceleration equals to V square by R, but V we have just found out that V equals to nothing but R into omega, where omega is angular speed. So this acceleration comes to be R omega square. Now we have a centripetal acceleration connected to this angular speed. Okay, one more thing. If this if this circular motion is with constant speed, then this moving body, which is on this circular path, this moving body will complete its revolution at a particular means in a particular interval of time. Let's say that time is capital T, which we call time period. If this body is revolving on this path, and then after time t, it starts its journey with the same. Let's say it is starting from this point A. So for each complete revolution, it takes time t, capital T. This time is called time period. And then frequency, if we ask what is the frequency of this body or particle of this revolution, so frequency we can write 1 by time period. Frequency is nothing but how many revolutions or how many cycle this body has been completed in unit time. So this we can write this way. And frequency we use to denote nu. This is nu, a Greek letter. If time period we are taking its unit as second, the frequency will be in units of per second, or we can write it hertz, and we denote it by Hj. So Hertz. This is frequency. Now we can proceed for angular frequency. The angular frequency will be nothing but here angular velocity, which we can write 2 pi nu. Now, why I am writing this thing? What is the difference between linear or frequency, simply frequency, and angular frequency? So, okay, let's take these two aspects. So, if this body or particle is completing one complete revolution in time, capital T, so in one complete revolution, this body has traveled a path length of 2 pi r, and this body has completed an angle of 2 pi. If we are talking about its angular position, it has been shifted by an angle of 2 pi in one complete revolution. So if we want to write the velocity we can write 2 pi r by time taken to complete one revolution or oscillation, we can say. And if we want to know its angular speed, in that matter, it will be 2 pi by t. And as we have discussed earlier, 1 by t is nothing but frequency, means the number of revolution it has made per unit time. Here we can write v equals to 2 pi r into mu. Not to be confused, this is for speed. This is actually a kind of Greek letter. We call it epsilon, and this is nu. So there is a very little difference between these two. Here we have smooth curve. Here we have sharp. So this is for speed. This is for frequency. So we can write this thing now. Angular acceleration. Oh, sorry, centripetal acceleration. This centripetal acceleration is nothing but v square by r. Instead of v square, you can write square of this thing, or with these two formula, you can write several different forms to get this centripetal acceleration. And one form I'm writing here that you can verify by yourself. This is 4 pi square mu square r. You can verify this equation by using these two things and in this equation. So for now, we are stopping here. In case you have any doubt, you can ask.